Good morning everyone. So today we are going to continue yesterday's class. So yesterday we have discussed about the fundamentals of membrane processes. So we ended up saying that there were four major categories of the membrane processes we are going to discuss in next two classes. So they were ultrafiltration, microfiltration, reverse osmosis as well as nanofiltration techniques, right. And also we are going to discuss about the electrodialysis as well. Okay. So if you remember a short recap, so we discussed about the membranes, so which is mostly of polymeric mostly, but there were ceramic membranes also we were seen, right. And also the another term is selective permeability. Selective permeability. So that means the membrane is having selective permeation. So that means it can allow only selected components. Selective permeability, or membranes allow selective components. Okay. So another important thing we talked about is transmembrane pressure. Transmembrane pressure, in that if it is a pressure driven membrane process, so this is very much important. Another one thing is we talked about tangential flow. So that means, so your feed is this is your membrane. So your feed is flowing parallel to the membrane surface, and the permeate is permeating through the membrane. So that means it is a cross flow, and the retentate will be collected here. Retentate. So this is a feed flow. So that is parallel to the membrane surface. Okay. So these were few important terms we have discussed, and also whatever we are going to discuss, what is that ultra filtration, microfiltration and nanofiltration and reverse osmosis. So all of them are pressure driven membrane process. Pressure driven membrane process. And also we are going to discuss about electrodialysis. So that is electrical field driven. That means the driving force is electrical field over there. So other than that, pervaporation is also there, but we are not going to discuss it in depth. Pervaporation, what happens is the vaporization through the membrane is a selective process. So the vaporization of molecules through the membrane surface is nothing but a selective permeability. So other than that, there are biological membranes. So which were used to retain cells and tissues. Okay. So this is the short recap. So now we are going to discuss about the pressure driven membrane processes, which includes all of microfiltration, ultrafiltration, nanofiltration as well as reverse osmosis. Right. In micro and ultrafiltration, the particle size is practically the sole criterion for permeation or rejection. So based on the particle size only, your permeate will permeate through the membrane, or retentant is rejected on the membrane surface. RO membrane separate particles at molecular level, right. So, reverse osmosis membrane separate particles at molecular level. Also their selectivity is based on the chemical nature of the particle, right. For other microfiltration, ultrafiltration, particle size is a sole criterion, but here the molecular level as well as the chemical nature of the particle is important in the reverse osmosis membrane. So, nanofiltration in essence the membrane process similar to RO, but it has also the overlap with the ultra and microfiltration. So, here are your operating pressure ranges. Normally in microfiltration it is 0.1 to 0.3 megapascal. Megapascal is nothing but 10 to the power of 6 Pascal. Okay, so into 10 to the power of 6 Pascal. Ultrafiltration is 0.2 to 1, nanofiltration is 1 to 4, reverse osmosis is 3 to 10. And in terms of particle size, limit particle size in the sense, so that is the particle size, beyond that it cannot allow, right. So, limit particle size which is in nanometers as well as molecular weight is also given. So, microfiltration is 100 to 10,000 nanometer the particle range which it can retain, and ultrafiltration is 1 to 100. If in terms of molecular weight it is a 10 to the power of 2 to 10 to the power of 6 Dalton, and nanofiltration 0.5 to 5 nanometer, and in terms of molecular weight 10 to the power of 2 to 10 to the power of 3 Dalton, and reverse osmosis 10 to the power of 1 to 10 to the power of 2 Dalton, but here it is solely depend upon the molecular weight of the particle, molecular weight of the particle. Okay. So, here it is a clear picture. So, where you can see clearly the particle size, based on that how your micro, ultra, nano and reverse osmosis membrane processes is categorized. So, if you see the microfiltration which removes the cells and debris, but it allows the protein. So, if you see protein has this overlap, right. It is not a clear cut definition, clear cut in the sense you cannot say all protein can permeate, and also you cannot say all permeate can be retained in the membrane surface, but cells and debris normally be removed. Then if you go to ultrafiltration, proteins and viruses, and it allows the sugars, but anyway there is no clear cut particle size range, right. Some of the protein particle also go into permeate, and some of the viruses are also pass through, that means permeate through. And nanofiltration mostly sugars, and also it can contribute to calcium ions, but if you go to reverse osmosis all are ionic levels Na plus Cl minus. So, this is mostly salt, that is why we use extensively in desalination of water, our reverse osmosis. Okay, so, microfiltration which comes 0.1 to 10 the micrometer, ultrafiltration 0.01 to 0.1, nano 0.01 to 0.01 micrometer, then less than 0.01 micrometer is nothing but your reverse osmosis. So, here is the tangential flow membrane process. So, you have a feed here. So, this is the membrane surface. So, this is the membrane surface, and your permeate is permeating through the membrane surface. So, this is the membrane, through the membrane surface your permeate is permeating, and the retentate will be inside the membrane, that is retained. So, that is collected later. So, if you see the feed is flowing parallel with the membrane, and your permeate flow is in the cross flow, that is perpendicular to the membrane surface. Right. And another important thing is that this transmembrane pressure difference, right. So, transmembrane pressure difference. So, this is the main driving force because these are all pressure driven membranes. So, that TMPD is nothing but the feed pressure is P1, and outlet when it gets collected, so that is P2. So, the average of these two is P1 plus P2 divided by 2, and P3 is nothing but a permeate pressure. So, that is minus P3. So, this is nothing but a transmembrane pressure difference, which is nothing but a average between inlet and outlet pressure minus the permeate pressure. And also remember what happens is when the feed is introduced into the membrane, so it contains solids plus for example, if we take the water with salts, right. So, salt water if we take, right. So, the water gets permeated through the membrane, right. So, what happens, the salt concentration will be increasing towards the end, right. So, this side salt concentration started increasing. So, what happens is after some time the flow rate of the suspension, right, it may not be high enough to drive the flow, right. So, in that case what happens, the salts get deposited, so it cannot flow further through the membrane to get it separated, right. And to avoid that, sometimes the normal process can be changed as the retentate is given back to the feed, right. So, to increase the suspension flow rate through the membrane. So, that is another criteria one may follow to increase the suspension flow rate when it passes through the membrane, to avoid the salt concentration which is not carried over by the normal suspension flow. Okay, so, here is the formula for your the permeate flux. J is here is nothing but permeate flux. So, this LP is nothing but a hydraulic permeability. Hydraulic permeability, and del Pm is nothing but your transmembrane pressure difference. Okay. So, this is the simple model. So, here what we use is the Darcy law. Darcy law in the sense you might have heard something like porous media flow. So, porous media flow is nothing but I have a channel, so in which the solid particles are there. So, normal velocity, normally if you see the pipe where your fluid is flowing, so there is no resistance to it, but when it sees the solid particle, so the flow will be somewhat reduced, the velocity of the flow will be reduced. So, it sees the resistance over that. So, the flow through these solid particle is nothing but the porous media flow, or sometimes the solid particle itself will have a pores in it. For example, so this is my solid particle, so it is a porous, so that also contributes the extra resistance. So, these kind of flows are called porous media flow. So, further the governing law is nothing but a Darcy's law. So, here also what we consider here is, so here we consider them as a capillaries, the membrane materials are parallel to each other. So, their radius is nothing but a r and it has the porosity of epsilon. So, from there the hydraulic permeability is derived as a epsilon r square 8 mu z. So, r is nothing but a radius of the capillary, epsilon is a porosity and mu is a viscosity, right. So, this has the unit of, J has the unit of meter per second, and LP has the unit of meter per second Pascal. So, your del Pm has 1 Pascal. So, both the side unit is conserved. So, Tm. Okay. So, the permeate flux is in meter per second. So, this LP, the hydraulic permeability depends upon many factors that we will see, but also here remember this is a model, right, Darcy law model we assumed, but there may be a restrictions to use this model based on certain assumptions. So, here we are assuming that as a Darcy law model and deriving this, right. There are certain restrictions to use these models that one should remember. Then the terms called sieving coefficient as well as rejection. So, the sieving coefficient is nothing but concentration of the solute in the permeate C perm and in the concentration of the solute in the retentate, that is nothing but C retentate. So, S is here is the sieving coefficient. So, for particles considerably larger than the widest pore, right, widest pore larger than, that is a rejection is total. So, that means S equal to 0. So, if the particles considerably smaller than the smallest pore are not retained, so in that case the sieving coefficient is 1, but for solutes with the particle size close to the pore size, then the sieving coefficients may vary, right. So, that means if I have a widest pore, my particles get in, or if I have a very smallest pore, my all particles will be retained. So, here it is 0, here it is 1. So, in between normal real operations will have sieving coefficients between 0 to 1. So, then rejection coefficient. So, rejection coefficient is nothing but 1 minus S into 100, that is very much obvious. The microfiltration membranes are specified by their average pore diameter. So, that is nothing but around 0.5 micrometer, but ultrafiltration membranes are characterized by their cutout molecular weight, which is nothing but COMW. So, COMW is the molecular weight of the smallest molecule retained by the particular membrane. So, for this purpose the definition is, how do I define the smallest molecule retained by the membrane? So, that is nothing but a retention coefficient of 95% is usually accepted as a total rejection. So, it will be said, for example, the cutout molecular weight of the cetine membrane is nothing but a 100,000 Dalton. So, then the next important terminology we need to be taken into account in the membrane separation processes, concentration polarization as well as the gel polarization. If we take the consider for example the ultrafiltration of a solution of protein. So, here assume the total rejection of the protein by the membrane and unrestricted permeation of the solvent. So, this is the ideal scenario. Okay. So, at the membrane surface protein is separated from the solvent, a protein concentration gradient normal to the membrane surface is created, right. So, due to which only the solvent is permeating, right. So, the protein concentration gradient normal to the membrane surface. So, for example, so here my protein as well as the solvent is flowing. So, the protein gets retained in the membrane surface and your solvent is passing through, permeating through, right. So, if you see the bulk concentration in the feed and the concentration of the protein in the membrane surface. So, I will put it as a Cp. So, the between Cp and Cb, so there is a concentration gradient is developing. The protein concentration near the membrane is higher in the bulk of the solution, is higher than in the bulk of the solution. So, that means when the feed is flowing along with the membrane surface, the concentration of the retentate from the bulk solution is moving towards the membrane surface. So, over the time what happens is the protein concentration near the membrane Cp is higher than the Cb. So, a distance away from the membrane. So, this situation is called concentration polarization, right. So, Cb is having lower concentration than the Cp, Cp is near to the membrane surface, Cb is away from the membrane surface. So, due to this concentration gradient there is a one point where Cp becomes higher than the Cb. So, this is nothing but a concentration polarization. And the high concentration at the upstream face of the membrane causes the osmotic back pressure. So, if you remember last class we told, right. So, the solvent moves through the membrane from the higher concentration to lower concentration, right. So, what happens? So, your in the membrane surface, so your concentration of protein started developing, right, the concentration gradient started developing. So, what happens? The solvent is permeating back, right, from the permeate side to retentate side. So, that is what the osmotic back pressure resulting in a backflow of permeate toward the retentate. So, this effect is not particularly significant in ultrafiltration as well as microfiltration, where the retentates are suspensions of solid particles or solutions of substances with relatively high molecular weight, hence low osmotic pressure. Actually, so this concentration polarization is very much dangerous in RO, right. So, because we told that there the retentate is mostly salt, right. The salts has high osmotic pressure. So, when to overcome that osmotic pressure, when the backflow happens, then that becomes a issue, right. But here this effect is not particularly significant, because the retentate here in this micro or ultrafiltration is suspension of solid particles or solutions of the substance with relatively high molecular weight solids. So, we need only less osmotic pressure only, but that is not the case with the reverse osmosis, where salts are having a high osmotic pressure compared to the solid particles or high molecular weight components. The concentrated and hence highly viscous layer at the membrane interface constitutes an additional resistance to the flow toward the membrane. So, once the concentration gradient is developing in the membrane surface, near the membrane surface, so it forms a highly viscous layer, because it is a protein concentrate. So, at the membrane interface, which constitutes a additional resistance to flow. So, it stops the, or it creates the resistance for the permeate through the membrane surface. So, the transport of solute at the upstream side of the membrane is composed of two components in counter current to each other. The first one is the solute transport from the bulk fluid toward the membrane surface. So, that means Cb, which is the bulk concentration, Cp is nothing but near the membrane surface. So, the solute should transport from the bulk phase to near the membrane by virtue of flow of solvent under the effect of transmembrane pressure difference. Then the solute transport from the membrane interface towards the bulk under the effect of concentration gradient. So, that is nothing but due to the concentration gradient, there may be a back diffusion. So, if you see here, yeah, this is what. So, what they were telling is, so from bulk concentration to near the membrane surface, it follows the convection mode. So, the solute is transferred from bulk concentration near the wall membrane, where it is here it is told as CW, and then the second one is the solute transport from the membrane interface toward the bulk under the effect of concentration gradient. So, this is due to the solute transport from Cb bulk concentration away from the membrane surface to near the membrane surface is due to TMBD. So, that is nothing but transmembrane pressure difference. The back diffusion of the solute near the membrane surface to the bulk is due to diffusion. So, that is due to concentration gradient. This is what probably in the last lecture we told. So, the pressure gradient, concentration gradient both affects the separation process here. So, at steady state the local concentration does not change with time. So, if the one steady state is reached, hence the two effects must be in equilibrium, right. So, the back diffusion as well as the convection of solute from the bulk to membrane surface. So, both are in equilibrium. Assuming fixed law for the back diffusion, the steady state condition can be written as follows. So, this equation. So, the fixed law of diffusion is nothing but fluxes minus DAB DC dx. So, this is nothing but a diffusion coefficient. So, this is a concentration gradient. And so, here it is J into C. So, J into C is nothing but a here this is a convection process. So, flux into concentration. So, flux is in meter per second. So, your concentration is in kg of protein per meter cube of solvent, kg of protein per meter cube of solvent. So, that means kg per meter cube. So, what you get is kg per second per meter square. So, that means, so kg per second is mass flow rate, per meter squared is nothing but a flux. So, this is a mass flux. So, that is due to convection. The other side, right, we told that both are in equilibrium. The other side, it is a minus d dc dx, because the diffusion process is governed here by Fick's law of diffusion, minus d dc dx. So, the c comes here. So, the d goes there, because the flux divided by d 0 to delta, delta here is nothing but a boundary layer for diffusion. So, dx equal to Cw Cb, Cw is a concentration near the membrane, Cb is the bulk concentration dC upon C. So, if you integrate, what you get is J is nothing but d upon delta, this is nothing but ln C, right, Cw Cb. So, this is J. So, this is 0 to delta. So, what you get is d upon delta. So, what you get is J equal to d upon delta ln Cw by Cb. So, this is d upon delta according to film theory. So, what you get is here as a mass transfer coefficient. Okay. So, this is K, d is in meter square per second. So, this is meter. So, this also comes as meter per second. Okay. So, the Cc get cancelled. So, J also meter per second. So, the unit is conserved. So, this is what the theory behind the concentration polarization and how to calculate the flux, right, solvent flux or permeate flux. Permeate flux from the concentration of the retentate near the membrane surface and the bulk. So, the next one is the gel polarization. So, what happens in the gel polarization we will see. If the flux is increased, that means the flux has to increase, then I can do it via transmembrane pressure difference, right. So, Cw increases accordingly, resulting in increased resistance to solvent flow toward the membrane. So, what happens here, the further I will increase the TMPD. So, then it increases the flux, and that is why the Cw is nothing but concentration of protein near the membrane surface, that increases and resulting in increased resistance to solvent flow toward the membrane. So, because of this getting, the layer is getting thickened and thickened, your solvent flow through the membrane is getting decreased, and this explains at least the partially the deviation of the membrane filtration rate from linearity. So, normally what we have is with respect to TMPD. So, I have a flux, this is a J is a flux. So, the line is linear. So, when you increase TMPD, the J also gets increased linearly. So, when gel polarization, so that means the Cw increases near the membrane, it also affects the linearity here, linearity between J and TMPD. The concentration of the protein in the liquid layer adjacent to the membrane cannot grow above the limit of Cg. So, this is nothing but a gel concentration, at which the layer becomes a gel. From this point on, the flux J cannot grow further and remains constant independently of an increase in pressure. Right. So, what we told, when we increase the transmembrane pressure difference, the J also increases linearly with TMPD, but there is a point where the concentration of protein near the membrane surface reaches Cg. How much ever I increase my transmembrane pressure, my J, the nothing but a permeate flux will not increase. So, this phenomenon is called as gel polarization. The gel concentration Cg depends on the protein and also the operation conditions, ionic strength as well as temperature. So, here I have taken an example of protein concentration, but that may be true for other filtration as well as the other materials as well. Okay. So, this is nothing but a gel polarization. So, this is what happens. So, this is the gelation layer. So, convection diffusion already you know Cb. So, this is near that it is nothing but a Cw, but now the Cw increases to the critical value of Cg. So, there your permeate flux has become constant, is become constant, or then further increase in TMPD you will not see any increase. So, this is nothing but a linear line, linear region. So, this is a transition, then after that your J becomes constant, J becomes constant. Okay. So, the shape of the curve describing the variation of the flux as a function of TMPD can be explained in the light of three models. The first one is linear model, where I told Darcy law. So, this is what I probably told here. So, this model only applicable when you are having a linear line. So, linear line in the sense J versus TMPD follows the linear line. So, there only you can apply the Darcy law model. That is what the restriction I told there. An intermediate flux segment, which is nothing but deviation from the linearity due to gradual buildup of resistance as a result of concentration polarization. The high flux is nothing but a saturation. So, this is a intermediate range, intermediate flux. Okay. So, the third one is the high flux where it is getting saturated. So, the gel polarization is the reason for that. So, practically constant flux, what it is independent of TMPD, even if you increase the pressure nothing happens to the flux. For a given set of material properties, KL is nothing but the mass transfer coefficient, whatever we have seen, that depends upon the tangential velocity. So, hence on the overflow rate through the module. So, it depends upon the tangential velocity, and the flow conditions which is nothing but a tangential velocity, turbulence, and system property, shape and dimensions of the flow channel, and material properties which is nothing but a viscosity, density, everything KL depends upon everything. Okay. So, these were few things we get to know before going to see different membrane process. So, today's lecture we probably cover two, which is nothing but a micro as well as ultrafiltration. So, here are the driving force for different membrane processes. So, based on the pressure we will have all four varieties what we are concentrated on, particularly in the food processing. So, pervaporation and gas vaporation separation also comes under pressure driven category. The concentration driven is membrane extraction as well as dialysis, and temperature driven membrane distillation process. Electropotential, electrodialysis, electroosmosis, probably we are going to see a little bit about the electrodialysis as well. So, this gives you the overall picture, right. So, the microfiltration, ultrafiltration, reverse osmosis, dialysis, electrodialysis, where it is used, what are all the membrane type, whether it is a symmetric membrane or what is the porous nature and what is the pore radius. So, pore radius already we have seen, and the driving force. So, everywhere the hydrostatic pressure, and dialysis it is a concentration, electrodialysis it is a electrical potential gradient, right. And method of separation, sieving mechanism due to pore radius and absorption, microfiltration we already told because the protein concentration, the sieving mechanism in ultra, and reverse osmosis solution diffusion mechanism, and dialysis diffusion in convention free layer, and electric charge of the particle and size in the case of electrodialysis. And microfiltration is used for sterile filtration and clarification. So, sterile filtration, the separation of micromolecular solution, that is nothing but ultrafiltration, separation of salt and microsolutes from solution, that is reverse osmosis, and separation of salt and microsolutes from macromolecular solution, that is dialysis. Desalination of ionic solution is using electric field, that is electrodialysis. Separation of gas mixture comes under the category of gas separation, but anyway we are going to concentrate only the first five. So, this is another in terms of the application, which industry, if your product is dairy, which one you choose, and if your product is juice, which to be chosen, and gelation and corn sweetener, sugar. So, this is also very minimal product only I have taken. You can further refer the reference and additional source I am going to give you at the end of the lecture. The application is milk concentration, whey concentration, whey fractionation, these we are going to see today, and lactose concentration, milk pasteurization, desalination, everything comes under the dairy processing. The milk, whey and whey concentration and fractionation, we use RO and ultrafiltration. The lactose concentration also RO, but milk pasteurization, microfiltration will be used, nanofiltration will be used for desalination as well. So, here whatever we have seen the different modules, right, spiral or tubular, hollow fiber, or one more is plate and frame we have seen, but that is not being used here. Most of the applications spiral membranes were used. And membrane here, the cellulose acetate membrane, which type of membrane we use? Cellulose acetate membrane, right. And TFC is nothing but thin film composites, thin film composites. So, lot of research is also going on in the suitable membranes for the various applications. So, this composite is now picking up the area. Composite is nothing but instead of one single membrane, so we will have advantages as well as disadvantages, right. So, to make these disadvantages into advantages, the another membrane is also sandwiched with this membrane to give the premium quality, right. So, that kind of thing is this thin film composite. So, then polysulfone, PS is nothing but polysulfone. This is polyester, PE is nothing but polyester. So, PVDF is nothing but PVDE. Yes. So, polyvinylidene diester. Okay. Then ceramic membrane, you know, yeah, that is all. Okay. So, here gives the which product and which application and which range of filtration technique with which module and membrane material I will be using it, right. So, this we are going to see mostly today, the milk concentration as well as whey concentration. Okay. So, now microfiltration. So, the microfiltration is alternative for dead end filtration as well as centrifugation. So, here you need to use lot of energy, but that is avoided when we use the microfiltration technique. In food industry, microfiltration is extensively used for the clarification of cloudy fluids. So, that means clarification of juice is the best example, clarification of juices. Okay. So, the membranes with the nominal pore sizes on the order of 0.1 to 0.5 micrometer or less produce permeates that are practically free of microorganism cells, right. This is what we told, cells and debris gets retained in the microfiltration operation. Microfiltration is being increasingly used for purification of drinking water and of water for the production of soft beverages. So, here we need the ultra pure water. So, there microfiltration technique is used. Food fluids clarified by microfiltration include clear fruit juices, wine, vinegar, beer and sugar syrups. So, the clarification operation can be done in fruit juices, wine, vinegar, beer and sugar syrups as well. Microfiltration frequently serves for the pre-treatment of fluids before ultra and RO, right. So, here see the membrane process is nothing but a filtration process, right. So, instead of directly going to ultra or RO, here the pore size used is 0.1 to 0.5 micrometer. So, more than that, whatever the bigger size molecules gets retained in the microfiltration technique, right. So, that is what it serves as the pre-treatment for the fluids before ultrafiltration and reverse osmosis. So, for example, so instead of directly going for ultrafiltration, so if I do microfiltration and go for ultrafiltration, my cells and debris get eliminated in the microfiltration itself, right. So, it is a pre-treatment for ultra and RO, and removal of suspended particles and colloidal material by microfiltration is essential for reducing the rate of fouling in subsequent ultrafiltration or reverse osmosis step. So, as I told just now, when you do this microfiltration operation, unnecessary these large size molecules gets eliminated here, but if it goes directly to ultrafiltration, unnecessary fouling or it gets clogged in the membrane surface. Okay. So, that can be avoided if we use microfiltration before ultrafiltration or reverse osmosis. Oil droplets and particles of fat, that is example is whey, are also removed by microfiltration. The membranes made of hydrophobic polymers such as polyvinylidene fluoride are particularly suitable for that application. Which application? Oil droplets and particulates of fat. So, when we wanted to remove these, so we supposed to use hydrophobic polymers, so which is nothing but a polyvinylidene fluoride. So, that as a membrane we can use in the microfiltration technique. And brines used in the manufacture of cheese and in fish processing containing suspended solids and fats, which must be removed before recycling or disposal of the fluid. So, this is not only used for direct food processing, but these techniques are used for the waste material which comes out of the food industry, right, because they have a high biological oxygen BOD. So, the waste disposal also it contributes. So, that is the one example here. Brines used in the manufacture of cheese and in fish processing contain suspended solids and fats, which must be removed before recycling or disposal of the fluid. So, before going for disposal, so that should be removed. That what is that? That brines. The suspended solids in the brines which is used for manufacture of cheese and fish processing. Other wastewater streams generated in food processing industry often require pre-filtration before further treatment as well as the disposal, right. There also microfiltration is used. The next is ultrafiltration. So, ultrafiltration mostly in the dairy applications. So, UF has become a major separation process in the dairy industry. So, this is very much important. So, if you see this here also, so the ultrafiltration, right, whey fractionation. So, these also whey concentration also we use ultrafiltration membrane. So, most of the application goes to dairy industry. The two largest areas of application are the pre-concentration of milk for cheese manufacture as well as the protection of protein concentrates from whey. So, this is the major two applications we are going to see for the ultrafiltration. The both applications are related to cheese making process only. So, if we see raw cow milk, I think we have discussed this in aseptic processing as well, I guess, right. The 3.5% protein and 4% fat and 5% lactose and 0.7% inorganic salts and remaining 87% is water, the raw cow milk composition. And in the traditional cheese making process, what happens is the milk usually after adjustment of the fat content, if any adjustment is needed, and after pasteurized it is coagulated through the combination of lactic acid fermentation or enzyme reactions. So, any one of the technique it is coagulated. After cutting and temperature adjustment, the coagulated mass separates into solid particles which is called curd and suspended liquid which is called whey. Okay. So, the curd contains major milk protein casein and most of the fat. The curd part contains the protein casein as well as the fat part. The whey is essentially a dilute aqueous solution of lactose, mineral salts and non-casein milk proteins, that is nothing but lactobulins and lactoglobulins. So, these are milk proteins in the whey, and the curd is subjected to various methods of treatment and cutting, resulting in the vast variety of different cheeses, and the whey whatever is left out, that is mostly used for the further processing, or most of the time it also goes as a waste. That is where I told, but the treatment process would be little bit expensive because it has a high biological oxygen demand. Okay, so, this is the traditional cheese making. After the pasteurization of milk, we will coagulate using any of the lactic acid fermentation technique or enzymatic reaction. Then the two things are separated, curd and whey. Curd is containing milk protein, casein and fat, and whey contains the aqueous solution of lactose, mineral salts and non-casein milk proteins. So, the curd is further processed for cheeses and whey is thrown out or sometimes used for further treatment as well. But in ultrafiltration, how we do this is, ultrafiltration of milk retains the fat globules and the proteins, the inorganic salts and the lactose along with some of the water, but partially removed as a permeate. Okay, so the same as that of traditional cheese making process, but the difference is the resulting retentate is a partially concentrated milk with reduced lactase and mineral content, and also the concentration ratio is often 3 to 5 fold. Okay, so that is the advantage, and if further reduction of lactose or mineral content is desired, then the retentate is diluted with water again and ultrafiltrate once again. So, this we call it as a diafiltration, and the pre-concentrated milk is mainly used in the manufacture of many types of cheeses, right. So, the concentrated milk whatever we got here, so that is used in the cheese making process. So, the advantage with respect to traditional making is the increased yield, probably because of the inclusion of some of the non-casein proteins in the curd, right. So, here we told in the traditional cheese making, non-casein milk proteins goes into whey, right, but when we use the ultrafiltration, so this also gets with the curd product itself, and low energy consumption compared to normal cheese making process, and reduced volume of whey, right, that is what I told. So, here almost 90% goes as a waste in the traditional cheese making process, but that volume gets decreased when we use the ultrafiltration. The fractionation of whey, this is another application which is done using ultrafiltration. The whey contains the major part of the non-casein proteins, right. So, the curd is taken and it goes for further cheese making. The removed whey, further we use fractionation technique using ultrafiltration membrane. So, whey contains the major part of the non-casein proteins together with low molecular solutes, which includes lactose as well as mineral salts. So, ultrafiltration of whey produces a valuable whey protein concentrate as the retentate and a protein free permeate containing mainly lactose as well as minerals. The retentate is usually concentrated further by evaporation or spray dried, and the whey proteins find extensive use in the manufacturing of cheese and a considerable array of food products in a health food specialist. So, that means the whey protein, further fractionating the whey using UF, so we will get whey proteins. So, that is further used for manufacturing of cheese as well. So, this is the flow chart where your microfiltration is first used. Here pre-treated as well as pasteurized whey, it is fed into the microfiltration, so which gives fat curd residues, and the whey further goes to ultrafiltration. So, we use diafiltration water here, if it needed second time it is ultra filtered. So, here what we get is ultra filtered permeate to lactose recovery, it goes further purification concentration as well as spray drying. So, whatever we get out of the ultrafiltration is nothing but a whey protein concentrate. The other applications of ultrafiltration includes clarification of clear or microfiltered fruit juices, and also if appropriate membranes are used. So, this ultrafiltrate juices are practically free of microorganisms. So, this is very much important. This we call it as a cold pasteurization or cold sterilization. So, based on the microbial load we can reduce cold pasteurized juices. Okay. So, this is especially, so this is juices are actually this is best alternative to thermal processing, but thermal processing your nutrients also get damaged, but here your nutrient value is retained, that is a advantage. So, if appropriate membranes are used, then we can cold pasteurize as well using ultrafiltration. The use of ultrafiltration for the concentration as well as fractionation of plant protein extracts are also suggested. So, that is nothing but a plant protein concentration as well as fractionation. Ultrafiltration is potentially useful in the process of isolated soya bean protein production. So, this is another important application of ultrafiltration. In this process, defatted soy flour is extracted with the water at high pH. The aqueous extract is then concentrated by the ultrafiltration. The flow sheet is here. So, we have deflated soil floor with water and alkali. So, that is pumped into the decanter. Based on the density, it removes the concentrated part. So, that is nothing but high density part. Then it further pumped to the microfiltration, then further ultrafiltration. So, here we get the permeate as a waste and the further processed with the ultrafiltration membrane using difiltration water. So, here we get the soy protein extract to precipitation and the permeate goes as a waste. So, this is the soy protein extract for further precipitation. And also the other application also include the sugars and other low molecular weight solutes may be also partially removed by repeated steps of dilution and diafiltration, which produces purified as well as the soy protein extract for further processing. And ultrafiltration is also used commercially as an alternative to evaporative concentration in the production of gelatin. So, these are also included in the ultrafiltration applications. So, here I will stop today's lecture, then we will discuss about the other two technique, which is nothing but nanofiltration and reverse osmosis in next class. And these are all the resources and additional references what I have used in this lecture. Thank you.